2141 Friday, week 4. What we started talking about this week in lectures on Tuesday, we started using the fundamental principles we learned in weeks 1, 2, and 3, and we said we're going to start designing some real circuits. We have been doing some examples on the Tuesday lecture of designing a couple of different things. Now, in today's lecture, what I want to do is introduce to you 4 of the really common design elements that we will be using when we design digital circuits. Those elements will be the decoder, an encoder, multiplexer, and a demultiplexer. Now, it's actually quite important to understand each one of them, what its operation is. And then it's also important to understand how we actually construct these things. Oi. Now, you will, in the future, when you're designing things, probably both in your labs and in the assignment. When the assignment, I'll probably throw at you some problem, and you're going to have to start designing from, whatever way you want. You will use those building blocks that we're learning now, and you do see them, in data sheets. You do see them as parts of bigger systems, and I'll show you what we can do with them. The first element that I want to introduce to you is a decoder. Now, very generally, a decoder is a circuit that takes n bits inputs and spits out up to 2 to the power of n outputs. Now, that's very abstract, but essentially what it does, it generates the min terms for all the possible combinations for the n inputs. Usually for most decoders, we don't see decoders that output less than 2 to the power of n. We will usually see n to 2 to the power of n line decoders. And that's what we call them, n to m line decoders. Examples, to give you some numbers, we might have 2 to 4 line decoders. So in this case, n would be 2. We'll spit out 2 to the power of 2. Larger decoders might be something like 5 to 32 line decoders. And the idea is that for the 5, in this example, for the 5 different inputs that you have, you can get any one of the 32 min terms, or pretty much all the combinations for all those inputs. Now, let's see what it all means. As an example, here's a 1 to 2 line decoder, and that's the smallest decoder you can really have. You have one input, A, and all the possible min terms, or all the possible combinations, are either A or not A. So we'll have n equals 1, so 1 input, 2 outputs. Now, one of the outputs, D0, will always output 1 when A is 0 and 0 otherwise, or when A is equal 1. And D1 will output 1 when A equals 1 and 0 otherwise. Doesn't seem to do much, does it? Let's have a look at slightly larger decoders. Here's, for example, the 2 to 4 line decoder. And this is when you start seeing a bit more of what it means to spit out the min terms for the different combinations. In this case, we'll have 2 inputs, A0 and A1. Now, you can look at the structure, and I wrote all the different outputs, and we have 4 outputs, D0 to D3. And if you look at the truth table, you can see that for each one of those combinations, the corresponding output will go high, will output a 1, where all the others will be zeros. So, for example, if I wanted to choose D2 to go high, for example, I will put in the combination 1, 0 at the inputs, which corresponds to a binary 2. And then only this particular output will go high, while all the other ones will go low. Now essentially, if you look at the expressions for these outputs, these are the mean terms for all possible combinations. So mean term 0, for example, if you remember the definition of the mean terms, is just not A1, not A0. And we can see that this will go to 1 only for the combination 0, 0. Any other combination that you'll try to put into it, it will zero it out. And this is sort of the property that we talked when we talked about mean terms. If you start thinking about this concept and you start expanding it into larger decoders, so let's say, for example's sake, 4 to 16 line decoder. You will have 4 inputs here, A0 to A3, and you'll have 16 different outputs where only one of them will always go high at any given time according to the input here. If I put a binary 7, for example, then D7 will go high where everything else will stay low. What is it good for? And it is actually being used quite a bit. Think about a string of lights, of LEDs if you want. Now when I was a kid, I constructed this little sort of roulette thing that corresponded to LEDs that kept, imagine that I can think, I'll just finish it off. Maybe there are 16 over there. It just kept going around. Now if I wanted to select only one LED at a time, I could have connected each one of them to a switch and then end up with 16 different switches. Or I can connect the outputs of the decoder into these things, and then I end up with only 4 switches, where every switch combination will correspond exactly to one light. So that's sort of one example of why you want to use a decoder. A more realistic example is if you have a computer memory. When we have computer memory, and you might think that we have, say, 4 different chips for the memory. Let's say each one of them is 1 kilobyte of memory, for example's sake. Now, we want to read or write for any one of those chips, but only from or to one of them at any given time. So usually those chips have what's called a CE input, and this is something you'll see very common in a lot of the chips you'll be working with. CE stands for chip enable. What this signal says is that when this signal is asserted high, and imagine all of them have them, then this chip will actually correspond to whatever instructions it's getting or whatever signals are coming into it. If this signal is asserted low, then anything coming to the chip will pretty much be ignored by the chip altogether. This lets us have a structure where we have a decoder that connects to those chip enables, where each one of them will correspond to one of the outputs from the decoder. And then we have a common data bus. Imagine this is a bus that is connected and shared by all those chips. Now if I wanted to write something into the memory, I would put some data here, but only enable the particular chip that I want the data to be written to. All the other chips, even though the signal will be connected physically to them, they will ignore whatever data was there. So this is a very good example of why a decoder would be useful. Because to select any one of those chips, you won't need 4 different sort of output lines, or well, you need 4 output lines, but you won't need 4 input lines. You can only have 2 of them to select one of 4. And this will also guarantee that only one of them will be enabled at any one time, because there's no way you can make this decoder output more than 1 at any one time. Now, there's a problem with starting to design larger decoders. 2 to 4 line decoder, it's a pretty simple structure. What we do is pretty much take the AND gates and have all possible combinations with the 2 inputs. So each one of those AND gates will have 2 inputs coming into it. If you think about, let's start with a 3 to 8 line decoder, where you will have 8 different outputs. Now all those different outputs will be the mean terms for the 3 different combinations. Mean terms for 3 combinations mean that each one of those terms will have 3 variables in it, which implies each one of those AND gates will have 3 inputs going into it for all the 8 different combinations coming from the inputs. Extending this idea, and if you go to really large decoders, then let's say we have 64, so 6 to 64 line decoder, then each one of those AND gates have to start having 6 inputs into them. Now we said that realistically, AND gates cannot have more than some number of inputs. 6 is pushing it, 4 we can do comfortably, 5 and 6 is pushing it. Once you get to 7 and up, it's pretty much impossible. Also, when we start having really large decoders, we are increasing the gate input cost by quite a lot. If you think about 64 different combinations or 64 different outputs, each one of them should have 6 inputs. 6 times 64 is a lot of gate input cost. So we need a method to build larger decoders that won't, well, first of all, they will solve this input, the many inputs into each AND gate, and will also try to minimize the gate input cost. So there's a method to do that by cascading decoders. We can build decoders, larger decoders, using small decoders cascaded together. Now, let me first of all show you this example, then I'll explain how you can come up with a decoder implementation for any number of inputs and outputs that you want. So in this case here we have a 3 to 8 line decoder, so obviously you'll have 8 outputs. Now in this final stage is combined from each one of those AND gates only have 2 inputs coming into them, but these inputs are a combination of something that came from 2 small decoders, so a 2 to 4 line decoder and a 1 to 2 line decoder. Now if you remember from the last slide, the 2 to 4 line decoders will give us all the possible combinations to A1 and A0. This 1 to 2 line decoder will give us the 2 combination for A2. Then ending all the possible combinations from this block here and this block here will give you the 8 combinations that you can have from 3 different inputs. So essentially what we're doing is we're taking the mean term and we're breaking it into, I'll give you an example because that might actually, if we had a mean term, say that looks something like this, what we're doing is essentially generating this, that's hardly an error, this half of the mean term using the 2 to 4 line decoder, the A2 we're generating it using this decoder, and then we're ending them together in this stage here. And this is the idea how you can implement larger decoders by breaking it into small decoders. Now in your lecture notes there's an explanation of the algorithm. I don't want to read it from the text, but I'll try to explain it to you verbally. So for any number of, or any size of decoder that you want to have, you take the number of bits that will correspond to this decoder. So in this case here, it will be 8 outputs. So it's a 3 bits decoder. And you try to break it evenly into 2 small decoders. Now 3 is an odd number, so we will break it into 2 bits decoder and a 1 bit decoder. If you had, let's go to a larger number, if you had a 64 outputs decoder, which correspond to 6 bits, then you will break the 6 bits into 2 small decoders, each one using 3 bits. And then those 3 bits, which is pretty much this structure here, the 3 bits here, will be broken down into 2 and 1. And then you can continue this idea until you get into either 1 to 2 line decoder, or, well, the 2 to 4 line decoders are essentially made of 1 to 2 line decoders. If you want to draw it as a tree, because that will be a nice way to present it, let's take some gigantic decoder. Let's take 8 to 256, which means we'll have 256 different outputs, which will be made of, now 256 is 8 bits. We break those 8 bits into 4 and 4, so those will be 16 and 16 outputs, which are made of 4 bits each. Each one of those 16 will be made of 4 and 4, which are 2 bits, and the same thing for there. And then each one of those 2 will be 1 to 2 line decoders until we get to this structure here. Now you can sort of verify that you've done the work right, because any break of the outputs should give you all the possible combinations for the sort of the parent node. So for example, 16 times 16, which will give you all the possible combinations, will give you 256 different combinations. Then if you break each one of those 16 to 4 by 4, then 4 times 4 is 16. You know you've done the work right, and then you can keep going. In this case here, all the numbers were even, number of bits. If you do have an odd number of bits, so in this case here 3, just break it into roughly even, so 2 and 1. If you have 5, then 3 and 2 bits decoders. Anybody confused? Anybody wants me to repeat that? Yeah?
So when you do cascade them, final AND gates at the end, you have to like manually calculate each one, right?
Well, there is a systematic way to do it. I mean, the whole circuit, if you're designing it yourself, then yeah, you have to connect all the wires yourself. But there is a systematic way of doing it. Even if you look at this one that I've got here, you'll see that from the top one, each one of those AND gates output, the first one will output to this one and to this one, the second one to this one and this one, third one here and here, and the fourth one here and here. So each one of them, you double the number of inputs. You double the outputs to different gates, and then you start outputting this into those gates in alternating order. So the not A will correspond to this, where the true form of A will go to here. So it's building up all the possible combinations. You can do it sort of in a binary fashion if you sort of write out the binary combinations, and then you can make sure you don't miss out on anything. So, yeah.
What's the bracket like?
These ones, these are the number of bits. So the way I wrote it is those numbers here are the number of outputs. In the brackets are the number of bits. So the way to read it, for example, the top one here will be 8 to 256 line decoder, which is broken down into 4 to 16 and 4 to 16 line decoder. The reason why I wrote the number of outputs is because then you can verify that you do get all the possible combinations, and you can verify that 16 times 16 is in fact 256. Yeah.
For the 64 outputs, which is 6 bits encoder.
Yeah.
Why do you break it into 2
The idea is to keep having each level AND gates with only 2 inputs in them. I could have, there's no reason not to break the 64 into 3. Well, we have 3 2 to 4 line decoders, but then that would imply that each one of those AND gates will have 3 inputs into them. Yeah, because you have 3 different structure giving you all the combinations. Now, doing it in this way will also minimize the number of gate input costs. Minimize or leave it the same. You could probably write it out as a proof and then calculate how many gate input costs you'll have for any different combination. You can come up with a formula for this and then prove that this will be having 2 inputs to the AND gates and then going back, breaking into 2 every time will give you the minimum number of gate input costs. Although if you did do it that way, the implementation-wise, you will get the same answer at the output. I mean, all right. Other questions? All right. Now, here's a bit of a problem. In the example that I gave you before with the 4 chips, then we said each one of them had a chip enable signal, and I could write to each one of the chips by selecting it first and then putting the data that I want into it. What happens while I'm changing the data in order to write it into a new chip? We said with the decoder structure that we have, there's always going to be one of them which is enabled. Now, if, for example, this one's enabled, and I'm changing the data because I'm preparing the data on the data line, and this is active, it will keep reading this data while I'm changing it, and I might start writing incorrect data into this chip. For example, if I wrote something here, and then the next time I want to write something here, then while I'm changing the data, this will read all the changes that I make before I enable this chip here. So I do need a way to have all of them disabled altogether. So something that will spit out zeros for any combination, for some combination of the inputs. And this is when we add an enable signal into our decoder. So we can take this decoder and just say, have another signal and enable into this decoder. Then when it's disabled, all of them will be zeros, regardless of whatever is on A0 and A1. So this might be such a structure. Now, if you look at this circuit, then you can identify that what we have here is just our 2 to 4 line decoder. All we've done is now taken all the outputs and passed them through an enabling circuit. Now, we discussed in last lecture what enabling circuits were. We said there are simply AND gates that when the enable signal is disabled, then all of these gates will now become 0, regardless of whatever's coming out in the outputs here. Which gives us this truth table there. In this case here, I've actually condensed the truth table. So when enable is 0, I don't care what A1 and A0s are. In fact, I do actually have 3 inputs into this circuit now, but instead of writing all the 8 different possibilities of those 3 inputs, I sort of enclosed 4 of those possibilities into one line because it doesn't really matter what A1 and A0 are. Because the output will always get zeros. When the circuit is enabled, we'll just have the regular operation of the decoder. Okay? Easy enough. Now, another thing we can do with decoders is in fact implement any boolean function that we want using a decoder. How do we do this? For example, take a circuit. This happens to be a 1-bit binary adder. And if you look at the truth table, the definition of a 1-bit binary adder, and we will talk about such circuits in week 8 or 9, week 9 I think. A binary 1-bit binary adder has 3 inputs. So we're adding together x plus y plus some sort of a carry in that comes into the circuit. Now, the outputs from this will be the sum of x, y, and the carry in, and it will spit out some carry out. At this stage, that's all I want to say about the 1-bit binary adder. We will discuss what carry in is, what carry out, and why do we need them. But essentially, this is just a truth table for some odd circuit that has 2 different outputs, C and S. As I said, C stands for carry out, S stands for sum. Now we can write those in the shortcut notation. For each one of them, the function S, where is it, is just a sum of mean terms. This function C is another function, sum of mean terms. Now, we said decoders actually generate those mean terms for us. And then we can have this kind of structure where we take the corresponding mean terms and we OR them together. Why does this work? Because this here means mean term 1 will just be not x, not y, z, or not x, y, not z, or x, not y, not z, or. So I just wrote the mean terms corresponding to these indices there, which are exactly what our 3 to 8 line decoder produces, because it does produce all the possible combinations. Once we pass all these mean terms through an OR gate, we essentially get just the function S that we want. And this is the same thing with the function C. I tapped into different outputs of the decoder, and I combined the different mean terms through an OR gate to produce the function C. One thing that's very important to notice, though, is how I connect those inputs here into the inputs of the decoder. In the decoder, it is implied here that this one will be the most significant bit. This one will be the least significant bit. And this is the same order I need to make sure that I've got from the function. So the function is defined such that x is the most significant bit. So I will connect it to this input there. Z is the least significant bit. I'll connect it up there. If I, for example, swap around x and z, I will get a totally different combination of mean terms at the outputs, and these functions will not correspond to what I want them to. So just make sure when you use decoders to connect, to build Boolean functions, make sure that the order of the inputs actually does matter. Don't just connect anything. Okay. That's what I got to say about decoders. Are there any questions about this before we move on? All right, let's move on then. The opposite of decoders, as you may have guessed, are encoders. So encoders do exactly the inverse operation of decoders. They take some 2 to the power of n inputs, where we assume only one of those 2 to the power of n will be 1 at any given time, and spit out the binary encoding of this particular bit that was high. So to give you an example, here's a 8 to 2, no, 8 to 3 line encoder. So we have 8 different inputs, and in this truth table, we assume only one of them will be 1 at any given time. And then it encodes the outputs, A2, A1, and A0, in their binary, in their corresponding binary form of whichever is 1. For example, if I'm looking at this line here where D6, the input 6 is 1, then the corresponding binary word will correspond to 6. Now we can actually come up with the expressions. We don't even need corner maps to write this thing out. In fact, we have 8 different inputs. First of all, it's impossible to draw corner maps on paper for 8 different inputs. But even doing it on a computer, it'll be easy. But trying to figure out the circuitry for this using corner map is not easy. But we could, just by observing this truth table, see that A0 will be 1 whenever D1 is 1, or whenever D3 is 1, or whenever D5 is 1, or whenever D7 is 1, which is exactly what I wrote in the expression here. Now this works because we know that everything else, when it's zeros, then all the other terms will be zeros as well. Now A1, same story. I will look at all the places where it is 1, and I will catch, what was it, D2, D3, well, D6 and D7, similarly to A3. And these will be enough to implement our encoder. Here's a problem if you do it that way. What happens if our assumption that only one of them is 1 is not true?
Make
What?
too many ones.
Sorry?
Bias yourself towards too many ones. So if more than one of those is 1,
Mhm.
you're going to get the same thing as you're already getting. You'll get a 1. But you may end up with several 1s.
End up with several ones where?
On your outputs.
And you have, well, let's see, for example, what happens, right? Let's assume, I don't know, that D6 and D3 are 1s at the same time. If this was our implementation, then D3 here will be 1, which will make this whole function 1. D6 in both these places, and there's D3 here as well, will make A1 and A2 1. The output that we will get is 7, which corresponds neither to D6 or to D3. So obviously, it's an unwanted result. What happens when none of the inputs are 1s? If all the inputs D0 to D7 are all zeros, and we look at this implementation here, then none of these will be 1, and then A0, A1, and A2 will be 0, which really implies that D0 is 1. So again, it's not quite what we want, because we want to encode some unique encoding into the inputs. How do we go about solving this? Well, we can define what's called a priority encoder. if we have a situation where more than one of the inputs is 1, then let's have a look at the most significant one and use this as our input value. So for example, if I had D6 and D3 on together at the same time, I will only look at D6 and say I want my output to be 6. If I had D1 and D3, 3 prevails and I want the output to be 3. So I need to find an implementation for this. The other problem that we had, what happens if all of them are zeros? We need to somehow convey to at the output that all the inputs were 0 and not D0 was 1. So you want to distinguish those two cases. And this is pretty much what I said. In order to solve all inputs equal to 0, and the ambiguity with D0 equals to 1, we'll add another output called a valid output, which will pretty much be a flag at the output that says at least one of those inputs is a 1, so output is valid. Or if output is invalid, that means that all the inputs were zeros, which implies this truth table. Again, this is a condensed version of a truth table, because here I have, for this 4-input priority encoder, I'll have 16 different combinations of inputs. But I condensed it because I know that once, for example, D3 is 1, it doesn't matter what the others will be, because this is the most significant one, and this will prevail, and I want the output to be 3 here, and it's a valid, it's a valid input. And this is true for all the other ones. As long as the most significant, the most leftmost is a 1, we don't care what's on the right of it anymore. The other case where all of them are 0, we'll now say, well, we don't care now what the outputs are, because we're saying that the output is invalid. So as long as we have some circuit connected to it that checks the valid flag and say, all right, if the output is invalid, then don't even worry about what the output is, then these could be don't cares. Now this one, I can't just look at it and implement a circuit. I will try to use corner maps to do it, but usually when we had corner maps, we had all the possible combinations. What happens when we have don't cares at the input, and how do we put it into our corner maps? Well, any place where there's a don't care at the input, it implies that this input can be either 0 or 1. So every don't care or every X that you have there implies this corresponds to 2 different possibilities. So this line here will correspond both to 0010 and 0011. And what we have to put in the corner map for both of them are these outputs there. Now, the more don't cares that we have for the inputs, the more combinations it will cover. If we had 3 of them being don't cares, this essentially covers 8 different combinations, all condensed into one line. So let's see how we put it in the corner map. We'll start off with what we know. So for the inputs 0, 0, 0, 0, and again I have 2 corner maps for the 2 different outputs. Valid, let's put it aside for a second. So 0, 0, 0, 0 in both of them will be this top left square. And in both cases, it will be a don't care. So for A1, don't care. For A0, don't care. The next combination, 0, 0, 0, 1, which will be 0, 0, 0, 1. So it's the next square down. Both A0 and A1 will have output of 0. So this is this square here. Then things start getting interesting. So for the combination of 0, 0, 1, don't care, we have 0, 0, 1, and then the don't care corresponds to the last bit there, which will correspond to those two squares together. So for this one, for A1, it will be 0 for both of them. For A1, it will be 1 for both of them, and these are this 0 here and this 1 there. Continuing this logic, for now for the combination of 0, 1 and then two don't cares, so 0, 1, and then we don't care about either of the two other bits, which will span this whole column here. For A1, the output will be a 1. So all this entire column will be filled with 1s. Where A0 will output a 0, all this column will be filled with 0. Now we really only have one more line. And as I said, 3 don't cares correspond to 8 different combinations, which luckily is what we have left. But to see how it's done, is that D3 is a 1, which is the case in both the columns that we have left. We don't care about the others. So A1, well, both A1 and A0 will be 1s in all places. And we'll just fill that with 1s and here as well. Now that's a pretty neat corner map because it's full of 1s. And we can actually group these things in quite large groups. So I've got one big group here of 8, then one big group here, and that covers all of them. For D3, I've got this one big group here, and for those two, I can group it and wrap around to here. Unfortunately, I can't make any larger group than that. For A1, this will correspond, because it's a group of 8, we'll have only one variable at the output. This one will be D3. This one will be D2, which is D2 or D3. For A0, we have D3, or the smaller group will be D1 or not D2, which is what I've got here. As for the valid flag, I really don't need a corner map for this, even though I could if I wanted to, because I can already look at the truth table. I can say, well, it's essentially 1 whenever any of the inputs is 1. So it's either when D0 is 1, D1, D2, or D3 are 1s. When all of them are 0, that's the only case that V will become 0 and the output will be invalid. So that's priority encoder. Usually we do use priority encoders more so than regular encoders, because with regular encoders you have to be really careful to make sure that only one of the inputs is 1, where priority encoders is defined to be the most significant input will prevail. Now, there's absolutely nothing to stop us to say that the priority is given to the least significant bit. In the same logic, you can say, well, the least significant input will be the one that we throw out at the output. Obviously, you'll have a slightly different design, but it follows the same ideas. That's about encoders. Multiplexers, I briefly mentioned it when we spoke about three-state buffers. The operation of a multiplexer is to have several different inputs and choose, using some selection lines, choose only one of them to propagate out to the output. In this case here, in this example, we have a 4-to-1 line multiplexer, which means we have 4 different possible information lines. So I stands for information. And to select one of 4, we need 2 bits for the selection lines. S obviously stands for select. And by putting whatever binary combination here, we can choose which one goes out to the output. Now, just to give an example where multiplexers might come in handy, first of all, in a lot of places, but think about a communication line. If you think about your mobile phone, I don't know how many of you actually know what technology your mobile phones work on. We work on what's called TDMA, time division multiple access, where on the same frequency or on the same channel, you're actually multiplexing few different calls from few different mobile phones at any given time, but you multiplex them in very small packets of voice from each one of those mobile phones. So essentially what happens, you have some circulating queue that picks a little packet from here, sends it on the communication line. Then it picks another one from another mobile phone, sends it on the same communication line, and then the third mobile phone, and the fourth mobile phone, and then it keeps going that way. So this is an example of a multiplexer where every time you just want to choose one of them and multiplex it out to the communication line. And this is how you choose which one you want. Now this is given in a truth table pretty much. For any selection that you have or any combination of a select line, you choose which signal go out to the output Y.
Sorry.
Yeah.
So I think this check is I1, I2, I3 mobile phone. So what is S1 and S1 again?
These ones, these are the select lines. So this is the sort of internal system, right? You can think that this is a base station, if you want, of a mobile phone, where this is the mechanics of the base station that just keeps selecting which one we want. So this goes from 0001, 1011, and keeps going. Shh, we're not finished yet. I will take another 5 minutes, so... Oh. That's because I let you go early on Tuesday, so it's only fair. Come on. And you gotta admit, it's a bit cooler today, so... So this is the idea... Shh. This is the idea behind multiplexers. How do we actually go and implement them? Well, we can use decoders to implement them. If you think about using a decoder for the select lines, what you end up with in this circuit here is something that will, sorry, that will be S1. So those terms in brackets are the mean terms that will come out of the decoder. This level of AND gates will end each one of those mean terms with the corresponding information input. And then the whole thing will be ORed together to give you this expression. Now for any possible selection that you have for S1 and S0, only one of those terms in brackets will correspond to 1. All the others will be 0. Now, for all those that are 0, the whole term, including the I, will be zeroed out, because 0 ended with anything is 0. And then whatever term, whichever mean term is actually a 1, for example, this one, will then be ended with the information line, I1, and therefore, the output will depend on what I1 is. If I1 is 0, the output will follow that 0. If I1 will be 1, the output will be 1. So this is essentially multiplexing and following only the selected information line. This is one way of implementing a multiplexer. Another way, which actually came up in the tutorial questions of this week, questions 17 and 18, is to implement the multiplexer using three-state buffers, where you only enable one buffer at any given time, and then you let the information line propagate through. Have a look at these questions, and then you see how it's all related. We could build larger multiplexers by cascading smaller ones. And the idea here is that if we break our select lines into the different multiplexers, we can select a few of the terms here and then let them propagate to the next stage, and then select from the next stage which one's propagating out. Let me give you an example of how this might be. If for the different I combinations, the selection criteria will be the binary combinations. So these will correspond to S2, S1, and S0 to select each one of them. What we're essentially doing is using the least two significant bits to select one out of groups of 4 of those possible 8. For example, if I wanted to choose I6 to propagate all the way to the output, 6 corresponds to 110, I will take S0 and S1, so 10. 10 will select something from each one of those 4 to 1 line multiplexers, so it will select this one and this one, and let it propagate to the output of the smaller multiplexers. Here we'll have I2 coming, and here we'll have I6 coming in. And then we'll use S2, the most significant bit, to then choose between which one of those we want. So in this case, S1 will be 1, and this will let I6 propagate to the output. Now you can take this idea and break this even to smaller multiplexers. You can have 2 to 1 line multiplexer here, and then break each one of those to another 2 to 1 line multiplexers in sort of a binary tree kind of way, where you break your selection lines where you have the most significant bits towards the end, and then as you go to the beginning, you start from the least significant bits. Very, very quickly, the opposite of a multiplexer is a demultiplexer, which does exactly the opposite thing. You have one information line, and you want to demultiplex it to one of many output lines. Now the idea is that the corresponding output will follow whatever the input is, where all the other outputs will just be 0. They won't be unconnected. It's not like a three-state buffer. They will just be a constant 0. You can see the truth table for any one of those input combinations. Then the corresponding output will follow the input I. Everything else is just 0. How do we actually implement this thing? Well, we already have. A demultiplexer is essentially the same as a decoder, only renaming the signals. Instead of, in a decoder, instead of calling this enable, this will be your information line. The 2 inputs will now become your select lines, and you have the outputs will correspond to the different Y outputs. Why does this work? Because having this input here in a decoder, we pretty much picked one of the outputs to be 1, but now we are only picking in the select line which one we want to follow the input or the information. The information is now connected to the enable, so that whenever the information is 0, then the whole thing is essentially disabled. And then whatever output follows the input is 0 as well. Otherwise, if the information is 1, meaning this decoder is enabled, then the corresponding output will be 1 as well, essentially following the information line. And yeah, that's that for the day. Sorry I went a bit over time. We'll see you on Tuesday next.